In this next video, we're going to explore the effect that a negative coefficient will have on a parent function. So given that we just graphed f of x equals the square root of x, I'd like us now to be looking at what about the graph of f of x equals negative square root of x? What happens if I have a negative coefficient here? So what I'd like you to do is pause the video, use the input values here that we did for the previous problem, and find out what the output values are. Once you've done that, graph that function here, and we'll look at what the similarities and differences are. Well, just like in the previous problem, the domain for this function is non-negative real numbers. So I need to use input values that are 0 or higher. So I will be using 0 and 1 and 4 and 9 because they're perfect squares. Right? When I input 0 into this function, I take the square root of 0 and then apply a negative, so it ends up being 0. When I have 1, I take the square root of 1 and get 1. But again, there's a negative coefficient, so that 1 output becomes a negative 1 output. Right? Inputting 4 will give me 2, but then the negative coefficient will make that negative 2. And finally, the 9 will give me an output of negative 3. When I go to graph these points, I have 0, 0, and then 1 and negative 1, and 4, negative 2, and finally 9, negative 3. And then just like we did last time, when you drew the graph for this, I hope that you did not go at all over into the negative input values. We cannot have a negative input value for this function, so our function begins here and moves to the right. So this is what the graph of f of x equals negative square root of x looks like. And my thought is there are some major similarities between this graph and the one that we just previously graphed, the first parent function for f of x equals the square root of x. And so the question that I would want to ask is, what are the similarities and differences between these two graphs? Right? Like, what do they have in common and what's different about them? So a few similarities I hope that you noticed. So one, they certainly both have the same shape. We already mentioned that. They also both start at the origin, and the fancy word for that is that they have a vertex, right? Their vertex is at the origin. So both of them have the sense of starting there and then moving to the right. And even that concept of moving to the right, what we effectively are saying is that they both have a domain of x is greater than or equal to 0. So there are definitely some major similarities between the two of them, but I think maybe what's more important is what are the differences between those two graphs. The two similarities and the two differences that stand out most prominently to me are first that the first function is above the x-axis and the second is below the x-axis. The next is this idea that the first one of them is an increasing function. The values keep getting larger and larger and larger, whereas the second is a decreasing function. The output values are getting more and more negative. They're getting to be smaller output values. So I really want you guys to have a good sense of both of these. When we have one function and then another function with a negative input, what we should notice is that they will have the same shape. They'll have the same domain. They'll start in the same place, but you're going to sort of see a reflection. One of them will be above the x-axis, one of them will be below the x-axis. If one of them was increasing, the other will be decreasing. We're going to see this pattern come up as we talk about these negative coefficients of parent functions. So now that we have a sense for these similarities, right, if we already know what the graph of f of x equals x squared looks like, can we predict what the graph of g of x equals negative x squared will look like? And I might actually ask you to remember that for a minute, right? What does f of x equals x squared look like? If we were to have a little unofficial graph here, right? In general, what does x squared look like? Right? We've talked about this idea that it sort of resembles a parabola that has its vertex right at the origin. And so what we're going to be exploring in this next slide is, what will negative x squared look like? And so, in some sense, an easy way to do this is for us to use an input-output table. So if I go through and use input values of negative 2, negative 1, 0, 1, and 2, right? If I go through and use each of these input values, input them here, square them, and apply the negative and get the output value, we can take a look at what we're going to get, right? F of negative 2 will be negative 4. F of negative 1 will be negative 1. F of 0 will be 0. F of 1 will be negative 1. And f of 2 will be negative 4. Right? I'd like to look at one of those briefly, this first one up here. When we compute f of negative 2, remember that what that's going to mean is I'm doing negative 2 squared. And remember your order of operations here. The negatives don't multiply and get rid of one another. We square first. You're going to have f of negative 2 being negative 4, which is where this value of negative 4 came from. So now if I take all these input-output combinations and graph them, I'll end up with negative 2, negative 4, and a negative 1, negative 1, then 0, 0, and 1, negative 1, and finally 2, negative 4. And hopefully we're not surprised by the graph that we see here. I missed that point. The curve that I end up with here is a parabola, but it's similar to the one that we had before. It's a parabola that's now opening downward instead of opening upward. The shape is the same, but the direction that the parabola is moving is different. It still has its vertex here at 0, 0, but it's flipped over the x-axis. So the last thing I want you to do in this video is I want you to predict what the graph of the function f of x equals negative absolute value of x will look like, and then check that prediction by making an input-output table. Okay? So pause the video and do that now. So for this one here, when we have negative absolute value of x, hopefully you remember that the absolute value of x function is sort of a v-looking function. And so the negative absolute value of x function we sort of expect to be reflected across the x-axis. So if I test this out by making an input-output table, we can sort of tell what's going to happen here. When I input each of these values into this function, the absolute value will make each of them a positive output, but then this negative will make each and every one of them change sign. So this here will be negative 2, this will be negative 1, this will be 0, we'll have negative 1, and we'll have negative 2. And so if I plot each of these points, we're going to see that the prediction that we made earlier turns out to be quite true. After plotting these 5 points, I can see that my graph is indeed the exact same absolute value v. Oops, just realized I missed on that point right there. It should have been there. We'll have the same absolute value v shape, but it'll be opening downward instead of upward. Again, this vertex is still sitting right here at the origin, but it's reflected across the x-axis.